For more than half a century, the language of Feynman diagrams has been our primary tool for both visualizing and calculating the interactions of particle physics. It's an incredibly powerful framework. But what if this language, for all its success, is merely an approximation of a deeper truth? In this discussion, we're going to examine a rather radical alternative, topological geometrodynamics. We'll explore its proposal to move beyond these abstract diagrams, replacing them entirely with the dynamics of pure geometry. Our path forward will be quite structured. We'll begin by revisiting the very bedrock of modern physics, quantum field theory, and examining some of the subtle yet profound cracks in its foundation. From there, we will introduce the core geometric postulates of TGD. We'll see how these ideas fundamentally redefine particle interactions, and then we'll unpack the mathematical engine that, in principle, makes the theory work. And finally, we'll address how this new framework purports to resolve one of the most persistent and, let's say, vexing problems in theoretical physics. All right, let us begin then with the established paradigm. For decades now, the undisputed calculational engine of the Standard Model has been, of course, quantum field theory, QFT. Now, the visual vernacular of QFT is, of course, the Feynman diagram. And one must appreciate that these elegant pictures are far more than mere illustrations. No, they are a precise pictorial shorthand for complex mathematical expressions. They are, in essence, the practical instructions for calculating how fundamental particles interact, scatter, and transform into one another. However, this incredibly powerful formalism is not without its challenges. There is a well-known and rather deep issue. You see, when calculations involve virtual particles, these quantum fluctuations, forming closed loops, the mathematics often goes astray. The integrals diverge, yielding infinite results for physical quantities, which is, of course, nonsensical. This divergence is a direct consequence of treating particles as dimensionless, zero-dimensional points. Now, to arrive at finite, sensible answers, physicists employ a procedure known as renormalization. It's a technique that has been phenomenally successful, yet one could argue it's mathematically, well, akin to sweeping a rather profound infinity under the rug. This ad hoc, though necessary procedure forces us to ask a very profound question. Are these diagrams and the ontology of point particles they represent truly describing reality at its most fundamental level? Or could it be that they are a remarkably effective but ultimately phenomenological approximation of a universe built not from points, but from something else entirely, perhaps from geometry itself? And it is precisely at this conceptual juncture that topological geometrodynamics, or TGD, enters the discussion. What it proposes is nothing less than a radical shift in our fundamental ontology, a move away from abstract mathematical points toward a physics founded upon extended geometric objects. So what is this central postulate? Well, in TGD, the fundamental object ceases to be a zero-dimensional point particle. Instead, it becomes a three-dimensional surface. It's best to think of it not as a dot, but perhaps as an evolving three-dimensional bubble or membrane. The trajectory, or what TGD calls the orbit, of this three-surface as it moves through time defines a four-dimensional space-time surface, and this entire structure is embedded within a higher-dimensional ambient space. You must understand, this completely redefines the very arena in which physics takes place. The focus shifts away from a single fixed background spacetime. Instead, physics unfolds in what TGD calls the world of classical worlds, often abbreviated as WCW. I want you to imagine a sort of infinite dimensional configuration space, a space whose points are not locations but entire four-dimensional space-time surfaces. Every possible geometry the universe could manifest is a single point in this grand arena. Quantum physics in this new picture becomes the study of the geometry and physics of this vast world of classical worlds. Now, this ontological shift from points to surfaces has, as you might expect, a direct and rather profound impact on how we must reinterpret the very nature of particle interactions. So let's compare. In the Feynman picture, an interaction vertex is an abstract point in space-time where world lines meet, governed by abstract coupling constants. In TGD, an interaction is a concrete geometric event. It's identified as the region where distinct four-dimensional space-time surfaces intersect. This intersection is a three-dimensional object, a sort of edge or singularity, a geometric defect where the very smoothness of the space-time surface fails. And this reinterpretation extends to the propagators, the lines connecting these vertices. In QFT, a propagator is a mathematical function that gives you the probability amplitude for a particle to travel between 2 points. In TGD, the concept is quite different. A propagator emerges as a correlation function, not in spacetime, but for modes of a spinor field defined on the world of classical worlds. It connects these geometric singularities, these edges, across the vast landscape of all possible spacetime surfaces. All right, this is an elegant geometric picture, to be sure. But the critical question is, how does one translate this into a calculable theory capable of making concrete predictions? This leads us directly to the mathematical formalism of TGD. One of the absolutely crucial principles that makes TGD potentially tractable is what's called the holography-holomorphy hypothesis. This is a very powerful conjecture. In essence, it states that the incredibly complex dynamics of these four-dimensional spacetime surfaces are determined, or holographed, by data on lower-dimensional surfaces within them. Now, why is this so significant? Because it has the potential to reduce what are typically intractable, nonlinear partial differential field equations into a set of algebraic equations. And if this holds, it opens the door to finding exact solutions, completely bypassing the need for the perturbative, infinite series of approximations that are the hallmark of QFT. This leads to a fundamental departure from the mathematical engine of quantum field theory. You see, the QFT path integral requires an integration over all possible field configurations or histories, including the virtual loops that lead to divergences. TGD replaces this entirely. The central premise is that physics is determined not by all possible histories, but by a set of preferred four-dimensional surfaces, which are analogous to the Bohr orbits of old quantum theory. Consequently, the problematic path integral is superseded by a well-defined functional integral performed only over the space of these preferred Bohr orbits, that is, over the world of classical worlds. And this really defines the new calculational paradigm. As Matti Pitkänen, the theory's originator, has stated, it is the action exponential, combined with this functional integration over the four-dimensional Bohr orbits, that defines the endpoint functions and the S-matrix elements. In other words, the core predictive quantities of particle physics are to be derived directly from this well-defined integral over the space of preferred geometries. So, after all of this geometric complexity and conceptual reframing, what is the ultimate payoff? Well, it is nothing less than the potential resolution of the very problem of divergences that has plagued quantum field theories since its inception. Let's draw a direct comparison. In QFT, you have divergent integrals arising from loops of point-like particles. In TGD, because particles are extended three surfaces, the interactions, these geometric intersections, are inherently smeared out. The singularities are softened. This means that the TGD counterpart of a Feynman loop diagram is proposed to be manifestly finite. There are simply no infinities that require cancellation via regularization. The truly profound implication here is the prospect of a theory that is intrinsically or manifestly finite. If this framework proves to be correct, it would render the entire elaborate procedure of regularization, for all its predictive success, an unnecessary artifact. It would become an artifact of what was, perhaps, an approximate point-based description of physical reality. And so we are left with a rather provocative thought. Is the ultimate language of physics really one of combinatorics, of abstract diagrams and infinite perturbative series that require artificial regularization? Or could it be something far more elegant, something more deeply woven into the fabric of reality itself? Could the ultimate foundation of physics be expressed not through diagrams of exchange, but through the dynamics of pure geometry?